I want to take a few minutes to discuss an idea that's used a lot in the next chapter, and then again in Calculus 2, and that's the idea of differentials. So say we have a function f. I'm going to draw a sketch of the graph y equals f of x. It's any old function. And here's my x-axis, of course, and here's my y-axis. I'm going to consider a point on the x-axis, which I'll call x sub 0. And what I want to do is move over a relatively small distance, and I'm going to give this distance two names. I'm going to call it delta x. Delta is often used to mean change in, so the change in x, but I'm also going to call it dx. So dx will look familiar because it looks like what's on the bottom of Leibniz's notation for derivative, dy dx. But right now we're going to treat it as an independent entity. So if we start off at x naught, we're going to move over by this distance delta x or dx. That means this x value has two names. We could call it x naught plus delta x, and we could call it x naught plus dx. So we go up to the curve, and this y value right here, of course, is nothing more than f of x naught. You plug the x coordinate into the function, you get the y coordinate. Let's go and draw in a tangent line at this point. So the line which just grazes, I don't know how good a tangent line that is. The line which just grazes the curve at the point x naught. Now we can work out the equation of that line. So we know the slope the slope of this curve is just the derivative at x naught. It's just f prime of x naught. And so now we have a point on the curve. We have the point on the line, I should say. Its x coordinate is x naught, and its y coordinate is f of x naught. And we have the slope of the curve. We have the slope of the tangent line, I should say, and that's f prime of x naught. And you can use any old formula. You can use the formula, say y minus y1 equals x minus x1, m times x minus x1, y minus y1 equals m times x minus x1, to get the equation of the line. So y minus y1 is f of x naught, equals m, which is f prime of x naught, times x minus x naught. And you could, of course, solve for y. We could get y equals f prime of x naught times x minus x naught plus f of x naught. And then I could multiply this together to get the equation of the line in the form that I'm used to seeing it. Now, I want to go over to this point, x naught plus delta x, or x naught plus dx. And I want to go up to both the curve and the line. And you can see that unlike at the point x naught, where the line is tangent to the curve, here we have two different y values. We have the y value on the curve, and we have the y value on the line. There's no reason they should be the same, but if we didn't move too far away, this should be pretty close. This distance between the old like the y value at x naught and the y value at x naught plus delta x, or x naught plus dx on the curve, we are going to call delta y, the change in y on the curve. So that's the distance between the y value at this point and the y value at this point on the curve. On the other hand, let me just sketch these a little bit further out. The distance between the y value on the line here and the y value on the line here, we are going to call that dy. And the main point is that delta y is approximately equal to dy if delta x is small. Of course, the smaller it is, the better that approximation is. The smaller delta x is, the closer the curve and the line are. So we could use this approximation to help us compute an approximation to delta y, how fast the curve changes. I'm not actually going to do that in this video, even though it is contained in this section. I will not assign homework on it, and I will not test it. I would like you to understand this basic concept. And this also gives us a new way of looking at Leibniz's notation for derivative, dy dx. Up till now, we thought of this as just another notation for y prime, and it certainly is. But coming up in the next chapter, we are going to start treating dy and dx as if they are separate entities. And you can see that in this picture, they are.